Okay, I want to start today with a comparison that, honestly, it feels kind of impossible to get your head around. It's one of those stats you read, you nod, and then like 5 minutes later, you're just staring at the wall and thinking, wait, what?
I have a feeling I know exactly where you're going with this. You're talking about the Google announcement, aren't you?
The Google announcement.
Yeah,
Specifically the numbers, 200 seconds versus 10,000 years.
that's the one. It is the statistic that launched 1,000 headlines, for sure.
So for everyone listening, let's just set the scene properly. This was back in 2019. Google comes out with this huge announcement. They've got this machine, the Sycamore quantum processor, and they say it solved this specific mathematical problem in just over 3 minutes, 200 seconds.
Right. And for context, this wasn't, simple math. This was a random number sampling calculation.
And then they drop the hammer. They claim the world's most powerful supercomputer at the time, a classical machine the size of a basketball court, would have taken 10,000 years to do the same thing.
It was a bombshell moment. It really was. It was the first real claim of quantum supremacy, which is basically the moment a quantum computer does something a classical computer practically can't. Not in a human lifetime, anyway.
Exactly. But this is where I hit a wall, and I think this is where a lot of people get stuck. That was years ago now. If we have technology, that is, trillions of times faster than our best supercomputers, why isn't it running the world? Why isn't there a quantum chip in my laptop?
Well, that's the multi-billion-dollar question, isn't it? Because you see a headline like that, and you just assume we've, crossed the finish line, that the tech is ready to go.
Yeah.
But the reality, we've basically just managed to turn the engine on for a few seconds without the whole car exploding.
So we are not at the flying cars stage yet.
Oh, not even close. We are entering what a lot of people are calling the end of the Silicon Age and the dawn of the quantum age. It turns out that the very laws of physics that make quantum computing so incredibly powerful are the exact same laws that make it nearly impossible to actually build.
So it's a paradox.
It's the cruelest paradox in engineering. The thing that gives you all the speed is the same thing that breaks the machine.
Okay, well, that is our mission for this deep dive. We aren't just going to talk about the hype and the speed. We need to explore why this is so incredibly hard, this whole battle against what they call noise, and whether we can actually bridge this gap between sci-fi and reality.
And to really understand that struggle, we have to understand the dream. And the funny thing is, the dream of quantum computing didn't start with a computer scientist in a lab. It started with a physicist who is just, annoyed with nature.
I love this story. We have to be talking about Richard Feynman.
The one and only. So picture this. It's 1981. Feynman is looking at how we use our computers to simulate the universe. He wants to model physics. And he just hits a snag, a really big one.
Because classical computers, the ones we're using right now, the phone in your pocket, all of it, they speak a very rigid language.
Binary, zeros and ones. That's it. Everything's a switch. It's on or it's off. Heads or tails. But Feynman looked at the universe, at atoms, molecules, electrons, and he realized something absolutely fundamental. Nature doesn't work that way.
Nature is messy.
Nature is incredibly messy. It's probabilistic. It's just weird. An electron isn't just here or there. It exists in this weird cloud of probabilities. So Feynman famously declared, nature isn't classical, damn it, and if you want to make a simulation of nature, you better make it quantum mechanical.
Nature isn't classical, damn it. I love it. He was basically saying you can't model the real world if your machine forces everything into these rigid little binary boxes. You need a machine that runs on the same fuzzy rules as the atoms themselves.
That's it exactly. He proposed replacing transistors with atoms. And just like that, the idea of the quantum computer was born.
All right, so let's get into the mechanics of this fuzzy machine, because this is where I think people's eyes can glaze over, but it's so critical to understanding the problem. Let's talk about a bit versus a qubit.
Right. The classical bit is easy. Imagine a coin lying flat on a table. It's either heads or it's tails. It's static. That's your 0 or 1.
Okay, simple enough.
A qubit, a quantum bit, is like a coin that's spinning on the table.
And while it's spinning, is it heads or is it tails?
Well, it's kind of both at the same time. This is what physicists call superposition. Until you stop the coin, until you actually measure it, it holds the potential of being both heads and tails simultaneously.
And that sounds like a magic trick, but that's where all the power comes from, isn't it? Because a classical computer has to check every option one by one, first heads, then tails. But a quantum computer can explore all these paths at once.
Precisely. But then there's another layer of weirdness that really just ramps up the power. It's called entanglement.
Ah, the spooky part.
Einstein himself literally called it spooky action at a distance. Imagine you have two of those spinning coins. Now, if they're entangled, they're fundamentally linked. If you stop one coin and it lands on heads, you instantly know the state of the other one, no matter how far apart they are.
Even if one is here and the other's on the other side of the galaxy.
Theoretically, yes. And this is what allows for this insane scaling. In a classical computer, you add more bits, you get a little more power, it's linear. But in a quantum computer, because of superposition and entanglement, every single time you add a qubit, you double the processing power.
That's exponential growth.
And it gets out of hand really fast. Just to give you a sense of scale, a quantum computer with just 300 qubits, which sounds pretty small, right?
Yeah, tiny.
It would have more possible states than there are atoms in the entire observable universe.
Wait, hold on. Say it again. 300 qubits can hold more information than all the atoms in the universe.
In terms of the states it can represent, yes, that's the promise. That's why everyone, governments, tech giants, you name it, is chasing this. It isn't just a faster computer, it's a completely different kind of math.
But okay, there's one more piece here, right? Because having all those possibilities is one thing, but you still need the right answer. If there are a billion possible answers and only one is right, how do you find it in all that fuzziness?
That is a great point, and it's often overlooked. The trick is something called interference. Think about noise-canceling headphones. You know how they work.
Sure, they listen to the outside noise and then they play the opposite sound wave to cancel it out.
Exactly, that's destructive interference. Well, quantum algorithms are designed to do the same thing. They create these interference patterns where all the wrong answers destructively interfere. They just cancel each other out. And the one right answer constructively interferes. It gets amplified.
So when you finally stop the spinning coins, the probability of seeing the right answer is almost 100%.
That's the goal. It's not just trying everything. It's a beautifully choreographed dance where all the wrong moves just disappear and the right one gets the spotlight.
Okay, so we have the spinning coins, we have this almost infinite power, we have the choreography. On paper, it works. So, why is this so hard? Why are we struggling to get past a few hundred qubits if that's all it takes?
Because keeping those coins spinning is arguably the hardest engineering challenge humanity has ever faced.
Why? What's stopping them?
The environment, everything. It's a villain called decoherence.
Decoherence. Sounds like something's falling apart.
It is. It's the quantum state falling apart. Think of it this way. Imagine you're trying to keep a whole room full of spinning tops moving perfectly in sync. That's your calculation. You need them all to stay coherent.
Okay.
But the environment around you is actively trying to knock them over.
Actively hostile.
It might as well be. A stray photon of light, a tiny vibration from a truck driving a mile away, a small fluctuation in the Earth's magnetic field. Any of these things just breathes on your spinning top and it wobbles and falls.
The spin stops.
The spin stops, the superposition collapses, and your beautiful quantum calculation just turns into classical junk. It becomes random noise.
So these qubits are basically allergic to the universe.
Terrified of it. And that's why if you ever see pictures of quantum computers like the ones from Google or IBM, they look like these incredible golden chandeliers.
They are gorgeous, very steampunk. I always wondered what all that gold is actually for.
It's mostly plumbing and shielding. That whole chandelier structure is basically the most advanced refrigerator ever built. They have to keep the quantum chip at temperatures near absolute zero.
Colder than outer space.
Much colder. Deep space is about 2.7 Kelvin. These machines run at millikelvins, just a tiny fraction of a degree above absolute zero, the point where all atomic motion stops.
And we have to do that just to stop the atoms from wiggling too much.
Exactly, because if they wiggle, the calculation dies.
But wait a minute, classical computers have errors too. My laptop glitches. We have cosmic rays hitting servers all the time, but we have ways to fix that. We use error correction. You just make backup copies of the data. If 0 flips to a 1, you check the backup, you fix it. Why can't we just do that with qubits?
And this is where quantum mechanics plays a really, really dirty trick on us. There's a fundamental rule in physics called the no cloning theorem.
I can't copy and paste a qubit.
You physically cannot. Think about it. To copy a qubit, you have to look at it to see its state. And if you look at it, if you measure it, what happens?
You stop the spinning coin. You destroy the superposition.
You destroy the very data you were trying to save.
That seems fatal. I mean, how do you build a reliable computer if you can't back up your data? That's like trying to write a novel on a typewriter that burns the page every time you try to proofread it.
It's a massive headache. The workaround is something called quantum error correction. It's a brute force approach. Since we can't copy the data on one qubit, We have to spread its information out across a whole web of other qubits. We use a ton of physical qubits just to protect one single logical qubit, the one that's actually doing the math.
So what's the ratio there? How many does it take?
It's daunting. Early estimates suggest that to get one single, reliable, logical qubit, you might need thousands of these physical qubits just acting as bodyguards, constantly checking for errors.
Thousands to one.
Thousands to one. So when you hear that we need a million qubit computer to, say, discover a new drug, most of those million qubits are just going to be for error correction. They're shields.
Wow. Okay, that really puts the scale of the problem in perspective. We're not just trying to build a chip, we're trying to build a fortress against the universe.
That's a great way to put it.
But despite all of this, the cold, the noise, the no cloning, we have built them. You mentioned Sycamore. So where are we right now? Are these machines actually useful for anything yet?
We are in a very specific and kind of frustrating era of history. The scientists have actually given it a name. We are in the NISQ era.
NISQ, what does that stand for?
Noisy Intermediate Scale Quantum.
Noisy is right there in the name. There's not great marketing.
It's honest. It basically means we have machines now, like Google's Sycamore or IBM's Eagle, that have enough qubits to do something interesting. That's the intermediate scale part. But they're profoundly noisy. They make tons of errors. They're unstable. They can't run a long calculation before decoherence just ruins everything.
So they're powerful, but really fragile.
Google's CEO, Sundar Pichai, actually used a perfect analogy for this. He compared that 200-second calculation to the Wright brothers' first flight at Kitty Hawk.
Right, that flight was what, like 12 seconds long?
12 seconds, and it went about 120 feet. Now, if you're standing there in 1903, you could easily look at that and say, that was pointless. You went 120 feet. I can't put passengers on that. That's not a solution to transportation. I can walk faster.
But that wasn't the point, was it?
No. The point was to prove the physics worked. It proved that heavier than air flight was possible. And that's where we are with Sycamore. It solved a problem, an admittedly useless problem designed just for the test, but it proved the machine works.
But there's a huge gap between a 12-second flight and a transatlantic 747.
A massive canyon, and that's what the source material calls the gap. We have these toys, these demonstrators, we need the tools. And bridging that gap, it's going to take a revolution in error correction to get us from noisy to fault tolerant.
So if I can play devil's advocate for a second, if it needs to be at absolute zero, if you need 1,000 bodyguards for one qubit, and if you're fighting the entire universe, why bother?
That's the cynical question, but it's the right one to ask.
No, really, why are companies like IBM and Google pouring billions into this? Is it just to be a little bit faster?
It's not about speed, not really. It's about complexity. The real prize is that there are certain problems that classical computers simply cannot solve. Not just that they're slow, they physically cannot handle the information.
Okay, give me an example, something real.
Let's talk about something you probably had this morning. Caffeine.
My lifeblood. I am running on it as we speak.
A classical supercomputer, the biggest one on Earth, cannot simulate a single caffeine molecule perfectly.
Really? A caffeine molecule doesn't seem that complicated. It's just some carbon, hydrogen, nitrogen. It's not like it's a strand of DNA.
But it has all these electrons interacting in complex quantum ways. To properly simulate the quantum state of just one caffeine molecule on a classical computer, you would need something like 10 to the power of 48 bits of memory.
10 to the 48th.
Which is roughly 10% of the number of atoms on planet Earth.
To simulate one molecule of coffee.
To simulate one molecule of coffee, it's insane. It's because nature is quantum. And trying to simulate nature with a classical computer is, and I love this analogy from the research, it's like trying to paint the Mona Lisa using only straight lines, using only toothpicks.
You just get a blocky approximation.
A stick figure.
Right. It looks rigid, it looks wrong. But a quantum computer, it paints with ink, it uses curves and shading, it speaks the native language of the molecule.
So if we can build these machines, we can finally simulate nature accurately. And what does that actually get us? I mean, beyond knowing more about my morning coffee.
Well, maybe the biggest one is nitrogen fixation.
Fertilizer.
Fertilizer. It sounds boring, but it is vital for our survival. Right now, we make fertilizer using a method called the Haber-Bosch process. It's incredibly inefficient. It uses high heat, massive pressure. It consumes about 2% of the world's entire energy supply.
2% of all global energy just to make fertilizer. That is a huge part of our carbon footprint.
It is, but here's the kicker. Tiny bacteria in the soil do this every single day, naturally, at room temperature. for free.
And we don't know how they do it.
We know what enzyme they use, but we can't simulate the chemical reaction because it involves all these complex electron transfers that are just too much for classical computers. A quantum computer could model that reaction perfectly. It could unlock that secret, and we could potentially make fertilizer with zero energy cost.
That would change the world. You're talking about feeding the planet and slashing carbon emissions overnight.
Exactly. Or think about designing the perfect battery chemistry for the solar age. Or drug discovery creating virtual labs, where we could test millions of molecular combinations without ever washing a single test tube. So instead of taking 10 years to find a new drug, we could do it in weeks.
That's the dream. That is why the investment is there. The hurdles are maybe the highest in tech history, but the payoff is its civilization level change.
You know, hearing all this deep desire to simulate nature, to understand the machinery of the universe, it reminds me that this isn't actually a new impulse for us. We've been trying to do this for a very long time.
Long before silicon chips, yeah.
I'm thinking of the Antikythera mechanism.
Oh, absolutely. The world's first computer.
For anyone who doesn't know this story, you have to break it down. It sounds like something out of an Indiana Jones movie.
It basically is. So, 1901, divers are off the coast of this little Greek island, Antikythera. They find an ancient shipwreck, and in there, among all the statues and coins, they pull up this lump of corroded bronze. For decades, everyone just thought it was a rock.
But it wasn't a rock.
Not at all. Decades later, using X-rays, scientists realized it was a machine, a complex machine with 37 interlocking bronze gears, and it dated back to around 100 BCE.
A computer from over 2,000 years ago.
An analog computer. You'd turn a crank, and it would simulate the cosmos. It tracked the sun, the moon, eclipses, the known planets. It was just unbelievable engineering for its time.
And think about the mindset of the person who built that. They looked up at the sky, at this complex, chaotic dance of stars, and they said, I want to build a machine that mimics that understands that.
And that is the exact same human drive that's building quantum computers today. The Antikythera simulated the orbits of planets. Quantum computers are trying to simulate the orbits of electrons. We're just zooming in.
We're trying to build a machine that runs on the same operating system as the universe itself.
That is the perfect way to put it.
So to bring it all back home, we've got this ancient dream simulating reality. We have the potential solving hunger, curing disease. But we're stuck here in the noisy era.
We're fighting nature's tendency to be chaotic. That's decoherence. We're fighting the fundamental rules about copying data, the no cloning theorem.
The hardware is fragile, the errors are high.
But the threshold has been crossed. I think that's the most important thing to remember. We aren't just building a faster calculator. We're not just adding more gigahertz to a processor. We are learning to speak an entirely new language.
The language of atoms.
Yes. And just like the Wright brothers, we might only be flying 120 feet right now, but we know it flies.
And that changes everything.
It does.
Before we go, I do want to leave our listeners with one final thought that came up in the research. And it's a bit of a mind bender.
I love a good mind bender.
So, some physicists have this theory that the universe itself behaves like a giant quantum computation. That reality, at its most fundamental level, is information processing.
From Quibbit idea, yeah.
Right. So if that's true, then by building these machines, by harnessing entanglement and superposition, are we simply hacking into the source code of reality?
That's a provocative question. Maybe if the universe is a computer, we're finally building a keyboard that works with it.
For everyone listening, next time you see a headline about a quantum breakthrough, don't just ask how much faster it is. Ask, did they manage to tame the noise? Did they keep the coin spinning just a little bit longer? Because that's where the real revolution is happening. Thanks for diving in with us.
See you next time.